Good morning, everybody. Thanks for joining our Ask Me Anything webinar in this October webinar. As you know, we do this time to time. And I know this time, like this year, and we have been doing many times since this COVID issues in all around the world. And it will be good to touch directly online with many clients. And I hope you can all hear me well, and you can ask me any question during this webinar. And you can just type your questions if you didn't already send it via email, and I'll try to answer that all today. I already received a couple questions, and I will start with those. But let me just go through. I prepared in some, based on some questions, prepare some slides, and I would like to start with this, our products introduction a little bit, and then I'll go through all these questions. So meantime, if you have any questions, just you can type your questions, and then I will answer all those. So we will be about 1 hour and talking and answering all these questions. Okay, you already know some of them. Know already our products, but I will just go through in all this, and let me see if any question here in the chat. Okay, if everybody's looks like hearing me, so no problem. So here's our first product is Minsting, which is the low power instrument. I mean the low cost also, that it has a 25 to 50 watt power output, is a battery, internal battery operated. It has been used many long time and for electrode manual measurement, and still you can use it for electrode manual measurement for Minsting instrument. It's good to have an internal battery, can go all manual measurement. It's almost a whole day. And second is the most powerful our instrument is the SuperSting, as you know. Has a different version, as like a 1-channel version, 2-channel version, 4, 6, and 8-channel version. So latest the model of the SuperSting is what we call it SuperSting, upgraded SuperSting R1, R2, R4, R6, R8, IP, SP, and Wi-Fi. So it has a, as you can see here, is a with Android application communication through the Wi-Fi. Sorry. In this Wi-Fi communication, you can control your instrument remotely, and you can see all this data on the field, and you can check your contact resistance. You can create also the measurement protocol on the field. You follow all these measurement apparent resistivity on real time, and you can make sure that your data quality is good on the field before picking up everything. So it will really helps to control the instrument, and also helps you to understand what you're measuring. This first thing, you can add it different modula what we created. We created, like, for example, marine modula. You can add SuperSting marine modula to do like a dynamic measurement on the marine and the lake and the sea, the ocean and the river. Either you do dynamic measurement, just towing your cable behind a boat, or you can towing your cable under the water as well. It also used for this marine cable together, SuperSting the instrument for stationary measurement. You can do that, like one of the stationary measurement, also or towing measurement can be also different version, what we call it deep ocean bottom studies, deep marine studies, SuperSting, also what we call it OBE1. So this is different type of the SuperSting version, and it's designed generally for deep ocean bottom studies. Maybe you have a let's say 500 to 1,000 meters in seawater depth, and you want to investigate underneath. So in that case, you need this deep ocean bottom OBE1 system. Another module for SuperSting is what we call it SuperSting Remote. This remote module is added to SuperSting. to do for long time monitoring, remote monitoring studies. So you like to monitor for example, between the boreholes for groundwater level or contaminations and any observation you would like to do, you can do through this remote monitoring option. You can set up your system in the field, and then you just set up that from computer, control your system anywhere from far from the field through the internet. So that like a remote module, what we added. Another is power sting module, what I will call it. Super Sting has 100 and 200 watt power output. It's good for many studies, and sometimes you may need the high power output. In that case, you can add this power sting module and Super Sting to make high power output, high voltage output on the transmitter in that case to do that study. So Super Sting can be used for generally with this, we have a passive system, active cable system. So when you do use passive cable system, you use switch box. This is here what you see, switch box or switch box script. So this is the generally is control all these passive electrodes. Another is the high power output switching is what we call it power sting node. So when you use like a high power output power sting, let's say 5 kilowatt, 10 kilowatt or 15 kilowatt, then for example 10 kilowatt, you can use these power sting nodes for high power outputs. So here you can see this passive multi-electrode cable. We have also a newer version of this, what we call it Flex Light, which is thinner and lighter for same quality with the earlier passive one, but this new one is easy to handle, what we call it Flex Light passive. So when you have a passive electrode system, you need switch box. And there can be stainless steel electrode or graphite electrode. If you're doing for salty water environment or water environment studies, and we recommend to use graphite electrode. If you're doing length type studies and any length studies, you can use also this passive electrode. So if you have a couple times of the, for example, borehole measurement or any water type of the measurement, especially fresh water, you can still use this stainless steel electrode. But if you're long time use for water environment, it is recommended to use graphite electrode due to oxidations, possible oxidation, and the curved electrodes. Another the electrode type what we have is called the active dual mode electrodes. These active dual mode electrodes can be a single mode or dual mode. It's generally we recommend this to use if you're doing generally for metallic mining investigations. So in that case, you can inject current through this metal output, and when you measure from just from the separate this point here, port of separate potential, especially non-parasitic that you're using, then you can measure your IP measurement, for example, through the from here. So you can see they have a manual cables, and we do also have our you're familiar maybe our Erdemir 1D, 2D, 3D, and 4D, and also 3D has a 64-bit version what we call Erdemir 3D SL command line version. So if you have a larger 3D layout, you can use Erdemir 3D and 3D SL. There's a different module. So whatever you need, any like a long marine studies, long line, and then you can add it module of what we call it CRP module, continuous restricted profiling module. If you're doing monitoring studies, you can add time-lapse module. So if you need any additional module, then also the software has a different module you can add. I would like to start with what the questions. So I received one question here. So what it's saying, AGI equipment I possess. So one of client has this Super Sting at 856 electrode, 6 meter spacing. Okay, so they use for 12 watt battery powering the system instrument with just 12-volt battery. So is this enough to conduct induced polarization from point of current strength? Application here, mineral expression. So any metallic mining investigations, okay? So that what you need to do, resistivity and IP. So there are a couple of things in resistivity IP. This instrument is sufficient most of the studies. So that like a marine module, for example, you have a very conductive environment, salty water. It works perfectly, super sting. Very clean signal. Cleanest signal you can find at the market with this is the super sting. So that's one thing. Another thing is like a mining studies. So in the mining study, what you need is inject more current. So you need to charge the ground with the higher current output. So you can think about this super sting has a 2 amp current output maximum, but this 2 amp current output cannot be injectable in the land. Only can be injectable in salty water environment. So that why the contact resistance. So that contact resistance is a key factor to do all these resistive studies, especially this resistivity in IP metallic mining investigations. So as long as you reduce your contact resistance, and then everything will work very good sense. So you will collect good data, you will inject good current in the ground, and then you will have a good signal strength, strong signal, and you will have also the good results always. So the first approach is always you need to improve your contact distance. And also I got another similar question is another client asking, how the suppressed effect of contact distance in sandy soil or desert area? So that's the same related here as the contact resistance. So let me just go through a little bit how we can improve contact resistance to able to use super sting as any this kind of the, let's say single box, let's call it transmitter receiver unit. So when you do instrument like a single box, you cannot put very high voltage outputs. You cannot make the instrument very powerful. Why? Because it makes this instrument in that case very noisable. So what you do is when I increase my the instrument power output transmitter, and I increase also internal noise of my instrument, then what I measure in the field, and I lose all my like a very small signals. And that's why we try to put super sting with optimal level of 200 watt power output with maximum 2000 milliamp, which is 400 volt. So, but with that one, I am able to get really good data. I will show you some examples that some clients has been done that for deep ocean bottom studies or metallic mining investigations, like a couple hundred, 200, 300 meters depth of investigation. I have clients has been done that for geothermal studies, more than 500 meters, almost 1,000 meters depth of investigation, just using super sting instrument. Some of them has been used that with one single battery with like a 100 watt power output. Some of them use 2 batteries, which is like a 200 watt power output in that case. So the clue is again is in these issues is the contact resistance. So let's just go through that what you do in the metallic mining investigation. First is in the as I said, you inject the current, you charge the ground. So like when you charge the ground and then you start listening the voltage. So that for listening the voltage, it will you get this IP effect from the ground. So our system works is the time domain IP. Okay, so we don't have low frequency like a frequency domain method at this moment. So we just focus everything in the time domain method. So another question was that same client was that. So I think that was answering that question. So what you're doing is injecting current, okay, and then turning off your current here. Then you listen. So what you strongly inject this current over here, and which is your primary voltage, and then decaying will be depending on how conductive your ground is. So we try to measure with this with 6 time windows. So some system in the market you may see maybe more time windows or different type of the time windows they can elaborate, but what is the main important is to get integration of this curve. So typically what we come up like a 6 time window is sufficient to get this integration. So this area, you can really get the area of this. So that will give you your secondary voltage. So as long as I get this secondary voltage, and then it doesn't matter, I have a 6 or 4 or 20, doesn't matter. So, but what we come up is for us is optimum way sufficient to get 6 time window. So I get this secondary voltage, and I already have primary voltage. Then this is the division, and what you get is chargeability. So what you're trying to get in the IP investigation is dischargeabilities. Okay, let's come back. This the thing is the contact resistance. So again, whatever you do, especially for metallic mining investigation, try to reduce contact resistance. Just the first rule is over here. Get this, we're using like about this stainless steel electrodes, stakes, and then you just put this stainless steel electrode all the way to the ground, like a 30-35 centimeters. And then in that case, what happened is you try to make this stainless steel electrode is touching the ground, contacting very well. It shouldn't be loose, okay? Has to be like a strong contact at the ground. So good contact is the first step. The second is, okay, if it is dry, you need to put water or salty water to make this the contact resistance is lower. So the new Super Sting has an application, Android application, permits you check this contact resistance easily. I mean, without that one also, any Super Sting check all this contact resistance. But what I mean is that you can by hand, and you can easily see with any on the tablet all these the variations, all those contact resistance measurement. So whatever you do, to start first to check your contact resistance, then try to reduce contact resistance. So how much my contact resistance should be reduced? Okay, so the rule of thumb is I always do is say this: when you do resistive IP, try to reduce contact resistance less than 2,000 ohms. Okay, so it is better to reduce less than 1,800 ohms. So if you're doing like a 2 batteries is a boost mode, you're using Super Sting, then make your contact resistance less than 1,800 ohms. But you may say that, oh, I have a contact resistance 30,000. So I did all these, what you're saying, water, salty water, and then put some, dig the hole, and then I couldn't reduce it. So there are ways to do it, always, okay? Here's the one thing is here. Here you can see on the first picture over here, is that there's a diaper over here, baby diaper. So there's a cement in the ground, and they just put this baby diaper top of this stainless steel electrode, and just try to increase, I mean, without using it, very huge contact resistance. So in order to decrease the contact resistance, they just put baby diaper and then put a salt, which is water, because this is the whole loss of the water, and then it makes moisture on the top of it. So it's able to inject some current. But sometimes this is not sufficient, but maybe this is just one electrode you did it. But if you're working such an area, there are like lots of all these is not permitted in this kind of archaeological study. On the left corner over here, and also right here in the video, you can see on the field, they are digging a hole, putting a water, and also putting this aluminum foil. On this left side over here, what they are putting is just like a what the medical, you know, the checkup when they do for electrodes, and they are using you know, conductive gel. So you can use conductive gel and this kind of the for example, the surface area ground, you're not allowed to dig, and then just put the gel a little bit under the electrodes and put it, the weight top of it. This reduce the contact resistance drastically. Just be careful on this one here. When you use conductive gel, generally is very salty. So if you don't have this graphite electrode, this type of electrode, it will be corrosive in the use. So maybe one time use is okay, but just clean up with the and all this salt and scratching a little bit with the sponge in the what you're using in the kitchen for cleaning in the at home. So you use that kind of sponge and clean up it very well after the use. But if you use always on this kind of things, and then just make sure that to use and maybe graphite electrode is good in this sense. And on the right over here, you just dig a hole over here, okay? And then this is typically for mining investigation, what they are doing on the right side here in the video. And they dig a hole, they put on water, salty water. This is like a current electrode location, okay? They put the aluminum foil and increase the surface area, and they connected two stainless electrodes, stakes together, and then put the top of it, the mud and water, and that's like a contact resistance is reduced drastically. So what is, for example, on this left one here, contact resistance was about more than 30,000, 50,000 ohms, okay? When they use the conductive gel, contact resistance reduced less than 500, less than 1,000 ohms. And right over here, also contact resistance was about 20,000, 30,000, 10,000, depending on the places. Some areas 5,000 or 4,000 ohms. In this case, contact resistance reduced less than 500 ohms. So there is always a way. So you may think about it. Yeah, but I don't have time to spend that much time on the field to expand all my current electrode location preparing like this way. Well, if you don't have time to do that, or if you cannot able to do that, so sometimes you may say, yeah, but this is soil. Sometimes you may have the area with the old rocks, so you cannot dig. Well, in that case, what you do, you put bentonite top of it, right? You just prepare like a bentonite. Instead, you don't have a soil, put just bentonite solution. And I got some clients in the Midwest region, they know very well. They have very, like a dry area and sometimes on the top, and they put bentonite and prepare kind of the hole, a little bit, dig the ground, put the bentonite solution, and then that keep the moisturized whole area during the, the whole survey day, sometimes 2 days. Again, if you don't have any soil in the area, you can put like a bentonite solution. So what I'm trying to say, the first step is always increase the current injection. How you do that? Decreasing contact resistance. So contact resistance is the key element to get the good data. So then you can really get this contact resistance lower down, and you can get it. So again, when you're doing metallic mining investigation, remember contact resistance should be lowering down less than 2,000 ohm or less than 1,800 ohm. Then supersting is perfectly okay. You can do maybe most of the mining investigation less than 500 meters depth. So it's perfectly good to use it supersting without any external transmitter. Okay, if you're in this case, then the client also has a power sting, external power. This is like an external power output, but they also did this, this way to prepare the current electrode location with supersting power output measurement. So once they did, and this kind of studies, here's like a typically the metallic mining investigations. And you can see depth of investigations about a couple hundred meters depth, 200-300 meters depth. So then supersting, just they use on this data, just use supersting, okay? They didn't use power sting. So including, I'm saying this client has supersting and power sting, but why they are having both. Because some area they couldn't reduce contact resistance, and then in that case they have to add power string modular, and then to increase the the current injection and power output of the instrument. So when able to reduce contact resistance less than 2000 ohm, they get this data with superstring directly. If you cannot reduce that, you can add it to power string. Here's another example from different client. Is that all this data is earlier one also on the top shows the resistivity up the section, and the bottom is chargeability section. So here you can see conductive zones and high chargeability zones more or less corresponding in these areas, mining areas. So this is another one also here, conductive and chargeability. So this is the typically what we're using is this kind of studies is metallic mining investigation is our dual mode multi-electrode system. So the question is, should I use this to do for this? While you're always doing metallic mining investigation, it is recommended to use this type of the electrode because it permits to measure from non-porous electrodes. You can see here non-porous electrodes, and then when you inject current, this electrode inject from here. When they measure voltage from here. So that's like what we call dual mode. So if you're doing always metallic mining investigation, we recommend to use this one. But if you're doing time to time metallic mining investigation, but most of the time is you're not doing, you perfectly use stainless steel electrode also. The thing is that you can use stainless steel electrodes without non-porous electrodes. There are the articles also, let's say, shows how to use stainless steel electrode without using non-porous electrodes. You can use it, and there are some polarization noise comes to. There is some polarization noise comes to in the stainless steel electrode, but sometimes it be ignorable. So in that case, you can use this stainless steel electrode without non-porous electrodes. But if you're going to use stainless steel electrodes, I mean passive electrode system with non-porous electrode, there are here two scenarios for you. You can just divide your cables in the half. If you have a 56, put on like two lines, parallel lines separated each other to avoid the crosstalks. You maybe if you have a 56 electrode here, if you have 112 electrode, another 56 electrode here. So like this parallel line is in the top, on the side is the stainless steel electrode, on the other line has a non-porous electrode. Or another option is to use the every single electrodes is a stainless steel, any odd electrode, for example, is the let's say non-porous electrode. So this way also you can use your passive system using together with non-porous electrodes. Okay. So this is the power string. This is the power string node. So when you need a very high power output, so that means your contact resistance cannot be reducible, or if you really need the high power output, then you can use power string for transmitter, external transmitter current injection. This one has a 5 kilowatt, 10 kilowatt, and 15 kilowatt version. So that means, again, super string is the 200 watt power output. This is starting 5,000 watt power output. So super string is very, let's say, operable in many environments, in many studies. As long as you consider keeping your contact distance, it will be, you can use it super string without any power string. And if you're really, there's also option to use power string with manually injecting current or automatically injecting current. So when you use automatically inject current, you use this power string nodes. Okay, then another question comes: how to spread effect of contact distance sandy soil or desert area? So this is the same thing what I show you that in the video, that in the sandy soil or desert area is it's good to use bentonite solution. Just to dig a small hole, put a bentonite solution, okay? But the thing is, when you have a sand dunes, that sandy soil is very thick. So maybe you got a 3 meters of 2 meters, 3 meters, or 5 meters sand dunes. In that case, you cannot use super sting. It is not sufficient because you have a very, very high contact resistance in this case. But maybe if you have a half a meter or less than a meter dry sand dune areas, then okay, you can use this, maybe make a very long stainless steel electrodes, maybe a meter, you just dig it, put it in the ground, or you just dig a hole and put bentonite solution and prepare this, and at least 1 day before you start measurement. So like you go over there, you mark all electrode locations, dig a hole, put a glass of bentonite solution. So it will wait maybe not overnight or 24 hours, that infiltrate through all these sandy ground, and then next day you may able to make some good measurement. Again, this is all depending on how thick your like a dry sand, like a special sand dune areas. So in that case, if you cannot do it, and then you need to use external power sting, transmitter power sting. So that will give you like a 5, 10, or 15 kilowatt power output as a different version, like a 1000 volt and to 2000, 3000 volt power out. It's a voltage output. In that case, you need like a high voltage output transmitter in this case. So again, if you're not able to reduce your contact resistance, then option is to use the external transmitter power sting, okay? So especially sand dune areas. So maybe if you're doing lots of studies sand dune areas, then it is better to consider to adding your super sting with power sting modular. If you're, again, let me emphasize one more time, that's important to reduce contact resistance. There's an option to reduce. If you're able to reduce it, then yes, you can use super sting. Another question is over here, which electric array is good for survey to detect fine and water? So this is the question, comes like this. So the question is, so which electric array is good to use for groundwater investigation? Okay. So you know, typically groundwater investigation can be in sediments or can be in fractures. So whatever you do for looking for groundwater is this looking for lateral variation, like here bedrock, here fracture, or sand gravel variations. So any lateral variation is important to find where the groundwater is located, or in any, not only groundwater, but any geophysical survey, electrical survey. So in this case, what we recommend always with our system, dipole. So dipole is the weakest signal you can get compared to other arrays. See, most of the instrument manufacturers, they don't recommend dipole. They already just go to Van der Schulenberger. Yeah, that's easy to do, Van der Schulenberger, because you're injecting current output, strong current, and then you get a strong signal, because all electrode, current electrode and voltage electrode are separated. So it will give you strong signal. But strong signal doesn't mean it's good signal always. Yes, good signal, but I mean the good signal gives you good information. So that's the important things. So like when you do dipole is very sensible to any lateral variation or also vertical variations. So in this case, what I am trying to get is in the field is all these variations. I am not looking for strong signal, but I need strong signal. I need a good information, gives me variations of underground. So I can get that with dipole. So if you have a super sting, you have to use dipole. If you have a different instrument, yeah, in that case, maybe dipole doesn't work, because some instrument doesn't have a good sensibility of the receiver. In that case, then doesn't give you good dipole. So then you get really noisy data in the dipole-dipole. But if supersting, you should do the first dipole-dipole. So as long as you keep your contact resistance, what I said, when you do resistivity, is less than 5,000 ohms. When you do resistivity IP, less than 2,000 or 1,800 ohms. In that case, you can really get good dipole-dipole measurement. Yeah, of course, sometimes there are some noise, cannot be controllable noise, like a geological noise, environmental noise, that really affect your measurement. Whatever you do, you cannot increase your noise level. In that case, still, I recommend to do dipole-dipole, or what we have also, extended dipole-dipole. So extended dipole-dipole or dipole-dipole, then you can add it later on. If you really see that still there is a noise data, you can add some gradient array, like a strong gradient. What we have is takes very short time, and then you can combine later on dipole-dipole and gradient together, make let's say the joint inversion. So here is an example of what you're seeing here is like a red color, and then let's say blue color, and then green color, right? Just consider like a color. I don't see that values yet. So what I'm saying is in this picture is the lateral variation. So you see how lateral change colors, like from red to green, and also from on the vertically. So that means is later on I check this value. So whatever is the groundwater in this, here you can see example, it's come from superstring array, 56 electrode, 5 meter spacing, and here shows dipole-dipole array. Okay, so you can really detect these variations. Okay, where you're trying to find the groundwater in this case. So that means if I do here Renner, I will not get this variation easily. I may lose it sometimes depending on the size and many things. So that in that case, okay, I got very good data Renner, but it doesn't help me to find what my target is. Then I drill over here, I don't get nothing. But then I really drill in this area. So that's the key point. So that how I can get it, a dipole-dipole. So another example is here is another example like a dipole-dipole again. This is like a combined dipole-dipole Schellenberger pole dipole array. So there are 3 array type combinations. So why they did pole dipole? To increase the depth. So you can see is the depth of investigation about 646 meters. So in here, and you can really see these variations. So there is a discontinuity of high resistive zone in here. There's a fracture over here. So that means this discontinuity gives a fracture. On the bottom, this should be the reservoir. Depending on the rainy season, dry season, the reservoir level will be, the water level will change. So then where it will show you this fracture location, and then it will show you where you need to drill. So it will, here's in the top, they have a contaminated water also showing. So if I drill over here and I get the all contaminated salty water on the first 180 meters depth, okay. Then if I pass this area, I really get here from fresh water. Again, dipole-dipole is the best things to do. You need to do the whole survey. Here's another fracture, still dipole-dipole, okay, with strong gradient. So they combine dipole-dipole. Again, what I said, sometimes if you get dipole-dipole a little bit noisy, just add it and maybe 5-10 minutes more gradient array, strong gradient. This can be prepared Erdimiger 2D, strong gradient array. So if you have our system, and then you can create dipole-dipole through the Erdimiger 2D or Superstring administrator, or through the tablet. So Superstring manager applications and the tablet. So you can create that. But strong gradient can be created through the Erdimiger 2D. Okay, here's a just question come. How about physical instrument for dipole-dipole array? Okay, since we're talking about dipole-dipole array, let's just answer this one before the other questions. Yeah, what I said is some instrument has they cannot do very well dipole-dipole. This is one of the instrument what you're saying. You may get some areas, but you may not get everywhere. There's the major differences. There are many the instruments in the market. So this is one of those. Is like if you get a signal about the 2 millivolt and less, and then that will be noisy for that instrument. But with SuperSting, you get a 0.02 millivolts measurement, so you can see our the spectrums and the technical spectrums, and also you can check for on our web page to all these case studies, especially marine studies. We have marine data. Is like you can get signals is like 0.01, 0.02 millivolts, very clean signal, best clean signal. All this dipole. So the dipole is some instrument, yes, it's difficult to get it. Some areas, yes, you may get it, but some areas, no, because the dipole has lose the signal when you go more than like 8 level. Okay, that's the key issue in our case, SuperSting R8. So we don't have SuperSting R10. Why? Like the one other instrument, yeah, they have a 10 channel, 12 channel, I don't know how many channels. But deep dipole doesn't permit you get more than 8 levels. So that's the key why we have a SuperSting R8. So the first thing is dipole. You may not get more than 8 levels. You may get noise in that case. Okay, so as long as you get further away or deeper and you lose the signal, dipole. And dipole signal is very weak also, but very valuable. So that weak signal has to be measured. Maybe sometime you may get 0.02 millivolts, 0.03 millivolts, okay, 0.2 millivolts. So dipole is like in that case is SuperSting can measure clean all these signals very well. But then sometimes in some instrument they cannot get less than 2 millivolts. Because less than 2 millivolts for them is noise. Why? But I said earlier, you increase some electronic design, some more power output instrument, you increase your electronic noise. Part of that, the SuperSting has 8 galvanically separated receivers. Some other instrument doesn't have that. Some instrument has just maybe 1 or 2 receiver inside. They use multiplexes dividing your signal mathematically in more channels, and then you can also lose your resolutions. So there are many parameters in this, but I don't want to get at that at this moment. Just want to show you may get it some area with your instrument, what you're asking, but some areas I don't think so. So that's why they suggest you sometimes to do a Venner or Schoenberger or gradient. Here, what is the best setup configuration get maximum depth for small area for length? Well, small area is, are you doing 2D or 3D? So if you're doing 2D, you can do pole-dipole to get more depth. Or you can do pole-pole to get deeper depth. So if you're doing 3D, it's the same thing, more or less. When you do dipole and 2D, if you're not getting the depth what you're interested in, because everything related to your cable length. So like a cable length is the determining parameter for depth of investigations. So if I have 100 meters, the cable length or area, because I can extend my cable on 100 meters, then my depth of investigation will dipole about 20%, which is 20 meters depth. But you want to investigate 30 meters. In that case, you can do pole-dipole. So you need to put one pole electrode is far away, which is about 5 times, 10 times of that area. So like I say, I have 100 meters area for cable length, then I need to put my pole location, infinite electrode location, 300, 500, or 1,000 meters away. So sometimes you may do it, sometimes you may not. If you have, then you need what you need, part of that multi-electrode cables, you need a single wire the cable to put your non-parasite, sorry, the infrared electrode far away. So that's one thing. If you're doing 3D, then 3D much easier in that case. So you just cover up like that area, maybe 30 by 30 meters square or rectangular area. Then you just lay out all your electrodes. Then you can just make this pole 3D array. Will give you like maybe 30 by 30 meters and 3D layout, and then pole 3D, it will give you about 30 meters depth. Okay, so that's the things you need to do. So the option is not much. The option is you can do is pole dipole or pole. If you cannot expand your area, sometimes, yes, I understand some areas you cannot do it, and then you're limited. So there's always limitation in some. So the other thing, how can I do a command file for 3D data acquisition on a grid? So this can be done in Erdemir 3D. Okay, let me see another question come up. How can I get more depth investigation for groundwater more than 1/3 of distance of profile? Okay, this is exactly the same question I just answered. Doesn't matter what you do, groundwater investigation, geotechnical, mining, depth of investigation is all related with your cable length. So how much your cable length will be, what we call a general maximum span. If I do dipole, my maximum span will be let's say is practically the total cable length, but a little less. Okay. So in that case, I always sponsor like practically your cable length will be good measurement, easy to calculate for depth of investigations. So between 15% to 20-25% is changing depending on the area. If I'm in the very conductive area like seawater, and my depth of investigation will be about 15, 16 to 19%, 20%. But if you're in the land area, then my depth of investigation will be 18, 19 to up to 25% on the dipole. So that will be but the average is about 20%. You can calculate always. You may get a little bit less, a little bit more depending on your area, study area. Okay. So doesn't matter what you do, including your groundwater, what your question is, your groundwater, you still can do that is to not the third distance of profile. I will say it is always 20%. Third distance, I mean the third distance of profile is 33. I mean, if you do pole dipole generally, okay. But if you're doing is the 5 times, you need to calculate. So I gotta go 5 times depending on the depth. So if I go 20 meters depth, I need to go expand 5 times. So okay, that's like a 20%. Okay, the question is the Erdemir 3D preparation of the command file. So this another question can come from same kind. Is the Erdemir the only possible if I don't have this software? Yes, I mean, let me just go through like this one here. Okay, here is the Erdemir 3D. Let me show you that first. Okay, and then you just go on Erdemir tools, and then we call it here 3D command creator. Okay, so depending on how many electrodes you have, okay, if you have like for example 56 electrode, and how many electrodes you're going to put in X direction, maybe I put 8 and Y direction 7. Okay, and then I'll show you this how to do it Erdemir, and then later I'll show you how you can do it with manually. But manually is you need to do yourself to somehow if you don't have Erdemir 3D. Okay, here's let's say just do maybe 5 by 5. Okay, and you can change orientation of cable also like this. Any setup like you can do. And this is the way. Okay, this is the geometry. Okay, this is the geometry. So like you can do this in Excel, this geometry. like all your address, okay, here. Okay, I can just grab this here. You can see here. Here is easy. You can see it's here is 56 electrode address, and then X coordinate, Y coordinate, Z coordinate, okay? And then here X coordinate 0. Like first electrode is coordinate 0, 0. Second electrode is 0, and Y is X is 5, Y is 0. So you need to do this geometry. This is geometry you need to create. Once you have this geometry, and then what you do is in here, easily, for example, like they say pole array, I said earlier. So just create it, and then it's done. Okay, so I can just save this comment file, and then just put it like here. Okay, and let me show you this what that comment file is. Just edit. Okay, now you can see this. This comment file has a header. Okay, if you don't have Erdimger 3D, you can send me. Then I can do it. Just maybe 1 or 2 you're doing. But if you need also the Erdimger 3D to do process the data. Okay, so if you have a different software and you can switch, it's time to switch for Erdimger to 3D also. I can give you a very good, reasonable change for that if you like to do that. So the first thing is the geometry over here. Okay? So once after geometry, here's your comment. Okay, what is this comment? Here's the first two is A and B current electrode location. So first electrode, since we're doing pole, second column, everything will be 0. Okay, so that means is I have using B electrode is infinity, and then A is B electrode current. So I'm injecting current between electrode 1 and 0, and then measuring from here between 2 and last one is 0 also. All the last is 0. Why? This is also the pole. So that means I'm measuring between electrode number 2 and infinity electrode. So in this case, you're doing this at P2 and P9. So this is the comment for each line. So if you like to do that for some systematically, you know how it idea works, and then you can do that. Okay, this is like comment like input create. So you can create this in Excel or MATLAB or any small maybe programming or manually. Okay, you just decide how you do it if you don't have any software. So this is typically this is the creating easily with Erdimger 3D. Okay. Okay. Yes, you will have the question comes, can I download the link of this video? Yes, of course. We will follow up later on once we're done with this preparing the video. All this the video recorded now is in this webinar, and then we will send you later on the link. You can watch it. Okay, another question. Can you please brief about how to overcome the problem of the shallow, highly saline groundwater? So what do you mean with that? So can you just explain a little bit more and just put me a little bit more? Can you, how overcome the problem of shallow, highly saline groundwater? So I don't see the problem over there. So the saline water is in the, let's say, are you doing this survey, let's say, contamination purposes? Because shallow saline groundwater, that means is you have a, okay, now it's writing. I'm talking about the quality. But saline groundwater level is okay. I know where you're located. For in the Middle East region, is you have a very salty water level that maybe sometimes is 30 meters and 30 centimeters in the depth. When you put in your electrode, you reach like a very let's say salty water in there. So in this case, is you have a very good contact resistance in the area. You have also very good current injection. But what happen is, in this case, if you have a very loss of the salt water level increase, and then you have looks like you're working on the seaside. So in that case, the depth of penetration, you should consider about 15 to 20% interval. Okay. So I will say it is about 18, 19% in this case, and 20% it will work. So it's not like a big differences. So if I go 100 meters cable length, so maybe then very salty water in the area, and then but in the deep ocean bottom studies, so where we have this, because we have like a very thick salty water, okay, like a deep ocean bottom. Imagine I am putting my cable on the top of the water at 50 meters salty water, or I'm putting under the water 500 meters under the water. So I have a 500 meters salty water. Then yes, there my depth of investigation 15%. But in your case, you're on the surface. Your salty water is in the ground, saturated. It's saturated water. In that case, your depth of investigation should be about 19-20%. So in order to increase your depth of penetration, then dipole is, I mean, you need to do dipole. Then you can combine later on in other array type if you like. But depth of investigation will not change with about 20%. Even if you don't have that area salty water, maybe then you may get 22%. So if 100 meters cable length, we're talking about 1 to 5 meters, the changes, nothing else. So that's normal. I think that answers your question. Yeah, I understand what you mean. Thanks for that question. So that's like a current penetration, not the current penetration, is the depth of penetration. So what you mean, right? So depth of penetration will change. So in that case, is the depth of penetration consider about 20%. Okay, is there? I think that's all the questions right now. I think I answered most. And let me just go through questions again. Yes, this is more or less what I answered all the questions. If I miss any questions, just please write me later on, and I'll be happy to answer also. So thank you all for joining our webinar today, and we will follow up later on for this recording. And if you have any other questions, just again, you can just write me, and I'll be happy to answer any question. Okay. Thanks, and have a nice day for everybody. I hope the COVID issue will end soon, and just keeping safe meantime, and have a nice day. Bye-bye.